Hey guys, we started discussing about the integral, right? And we defined a partition of a closed interval a b. I think you remember we did last time, right? That means if you have closed interval a b, you split this interval into finite number of subintervals like this. So here you have finite set. This set is a finite set, right? You split this interval AB into finite subintervals, right? And if you take the union of these subintervals, what would you get? You would get the interval AB, the closed interval AB. If you take the union of these subintervals, you get the original closed interval AB, right? And we define, so this delta x sub I is defined by the width of 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 this interval here, right? This interval, right? So here, so just note that. So this is very important. In this course, talked we just focus only on continuous function on closed interval. That means you can find maximum value of f and minimum value of f over the given interval, right? That's why we are focusing on continuous functions on closed interval, right? So we define upper sum of f corresponding to this partition P, which is given by this thing. You remember that. So so so, so this is the upper sum. So what is, so now consider this interval AB, right? You split that interval into three subintervals, 1 2 3, right? And if you consider this subinterval, the maximum value of the function is near here, right? So this rose color rectangle gives you the area of so that one. So if you complete this rectangle, right, this one here, uh-huh, so you can find uh, the area of this rectangle, right? Which is, so suppose the maximum value of f or on this interval is capital M sub 1. So the height is M sub 1 times the width of this subinterval, which is x sub 1 minus x sub 0, right? And similarly you can consider this subinterval, right? So the the maximum value of f of over this interval, say M sub 1, right, nearly here, right? So if you complete a rectangle, this one, you can find the area. The area is given by M sub 2 times the width of that rectangle, x sub 2 minus x sub 1. Similarly, you can sum them up, then you get the lower sum of lowest no upper sum of f corresponding to this partition, right? Similarly, we can define the lower sum uh, of f corresponding to p by finding the minimums. So if you consider this subinterval, this is the minimum. Let's denote it by m sub 1, m sub 2. So height of this one is m sub 1 times the width of this rectangle. m sub 1, simple m sub 1 times x sub 1 minus x sub 0, right? Similarly, you can find the minimum of this interval, minimum of this function over this interval, which is nearly here, right? This height is a simple m sub 2 times the width of that rectangle, which is x sub 2 minus x sub 1. Like that, if you sum them up, you get the lower sum of f corresponding to that partition. Right? These are the definition of lower sum and upper sum of f. Right? And this is clear. I think this is clear to you, right? So, and the other thing is upper sum is always bigger than the lower sum. That is very important. I think this is trivial, right? And if you consider, so here, if you consider two partitions, P and Q, but Q has many points than P, but P is a subset of Q, right? So in this case, what happened to the lower sums and upper sums? The lower sum is increasing when you add points, but upper sum is decreasing, right? So this one here, this is very clear. I think if you look at, I think I explained this concept to last week, right? So here, so as I said before, we mainly focus on continuous functions on closed interval in this course, right? So not that we mainly focus on continuous function on closed interval, right? So look at this definition. This one is very important now. I think you have to find integrals using this definition, right? Here f is a continuous function on a closed interval AB. Yes, alright. And there is a unique number I that satisfies this inequality, right? The lower sum is smaller than that number I, and that number is smaller than the upper sums. So this I is called the integral. This is a unique number. There is only one. There exists a unique number I such that this inequality holds, right? Such that this, right? For any partition, for each partition. So this unique number is called the integral of f. Integral of f over AB, which is denoted by this integral of f over AB integral. So this is basically this is I. So let's do some examples using this definition, right? So let's try to do this example. So you have a constant function. Let's do this problem here. So you have a constant function here. Look at the function here. F of x is defined by this number. So for all x in between a and b, right? And show that the integral of f over ab integral is given by this. So let's try to do this problem. We have a function, a constant function f of x. Oh, wait a second. Okay, have function f, so which is a and the function value is a constant value k. F is defined over this interval. Right? Let's say this is our interval AB, and the function value is constant k. And clearly we know that the integral of f over this interval means the area under the curve bounded by this interval, which is k times b minus a, which is clear, but we have to prove that using this definition. So let's consider any partition P of this closed interval AB. Let's consider, let P, capital P, be a partition. So this is the initial point of this partition x0. This is your x0 and x1, x2, x, say xr, right? This is the last point. X sub n, x1, x0 is smaller than x1, right? x2, and final point is xn, which is same with b, right? Here x0, where x0, x1 is less than or 2, x2, like that, right? This is the end point of that interval A. This is the other end, which is B, right? Let's consider any general partition of this closed interval, right? AB, right? Then let's consider any general subinterval. That means, so here what we did was we split this whole interval into small subintervals, right? Small subintervals. So let's consider a general subinterval x minus 1 comma xr, this interval. Consider this subinterval, right? So over this subinterval, you know, this function is a constant function. This function is constant. The maximum value and the minimum value of the subinterval of the function over this subinterval are the same. Let's so capital M sub r is equal to simple M sub r, and that this one is equal to the function of constant value k, right? Then let's compute the lower sum of f. Let's compute the lower sum of f. Lower sum. So we use notation. It is denoted by u of lower sum of f corresponding to our general partition P, which is R goes from 1 to n, and this is M sub R delta x. That means width of this general subinterval. The width is x sub R minus x sub R minus 1. The width is x sub R minus x sub R minus 1, right? So we know that the maximum value of function f o on this interval is the same, which is k. For each subinterval, maximum value is the same, right? Maximum value is the key. Sum goes from 1 to n. The maximum value is the same, x sub R minus x sub R minus 1. So let's pull out this constant k from the summation mark. Let's pull out this constant in front of summation mark. 1 to n x sub R minus x sub R minus 1. So if you expand this sum here, what do you get? If you expand this sum, k is common. Let's put a bracket, right? The first one is x1 minus x0, x1 minus x0, and the second term x2 minus x1, the term before the last term, the term which is before the last term, x sub n minus 1 is x n minus 2, the last term x n minus x n minus 1. You can simplify this one also. This one cancels with this, and this one cancels with this, and this one also, and this one too, right? So you end up with having k is common, k inside this square bracket. You end up with having x sub n, which is same with the endpoint. So x sub n, what is x sub n here? B, right? B. X sub n is b. Let's write x sub n negative x sub 0. K x sub n is b minus x sub 0 is a. I think you remember that. X sub 0 is equal to a. So this is the upper sum of f corresponding to partition P. Upper sum of f corresponding to partition P. Similarly, using this definition, using the definition of lower sum, you can compute lower sum, which is also same k. You can calculate this, right? To yourself, right? You get this one. You would get this. We know that. We know that the integral of f over ab in between upper sum and lower sum. So the upper sum, if you take any partition, you get this upper sum, right? If you take any partition for general partition, you get this value here. So upper sum is k times b minus a, and the lower sum is the same value, and these two values are equal. That means this integral should be equal to this value. That integral of f over a b interval should be equal to k times b minus a. Right? So this is the proof. So this is the proof using the definition of integral, using this definition, definition here. Right? Now can you do this one? So this time f of x is defined by x here. F of x is x over the closed interval. Show that integral of f over a b interval is given by this. Can you do these two questions? I will help you with these two questions in my next video. Right, see you next time.